I'm recording. Sorry about this, guys. Friction is always opposing motion. That's what the force of friction is doing, right? You need to overcome that force of friction, or you need to be constantly overcoming that force of friction to have motion. So it's parallel to flat surfaces, tangent to curved surfaces, and opposite of motion. The other things is it's dependent on the force that presses surfaces together, right? So like you can generate friction if you take your hands and lightly rub them together, and then you apply more force, right? You can feel that friction generate warmth in your hands, right? With higher force, more so than with lower force. And in the scenario of the most cases we're going to be looking at, that force that's pressing things together deals with gravity, right? You've got a force of gravity and you've got a normal force, equal and opposite the force of gravity. That force of friction depends on this normal force. Now, for a horizontal plane, the normal force is equal to the weight of the object, right? We're going to look at some scenarios where our surface is angled, right? In that case, our normal force is not equal to the weight of the object. We have to account for the angle. Yeah, generally, it's independent of the area of the surface of contact. So the friction itself is usually given as a coefficient, and we'll look at this in some detail here. Independent of velocity. Again, all the problems we're dealing with here, we're pretty much saying, well, we're simplifying it. We're not worried about any velocity independence. If you deal with aeronautics, particularly things like aeronautical engineers, have to worry about the fact that the faster you go in air, because of compression forces and the nature of travel through a fluid, you do have friction increasing with speed, particularly as you get to really high, close to the speed of sound or above it, right? You got a whole bunch of different phenomena, but in general, we're saying it's independent of velocity for most of the cases we care about. But it is dependent on the nature of the surfaces, right? So this is just demonstrating that you've got, because of part of the reason you have friction, right, is because these surfaces have a roughness associated with them, right? They're not perfectly smooth. So if you're sliding a crate on, I don't know, a floor of concrete, that's going to be different than sliding the crate over, I don't know, a sheet of ice, right, or a carpet, right? Those different surfaces are going to have different frictional forces just by virtue of the materials they're made out of. Let's see. All right. Oh, yeah, free body diagram. So this is not too, I mean, it shouldn't be that much more of a stretch from what you were working on before, but if you have an object resting on a surface, right? If you remove that surface, you're replacing that with a reaction force. Well, in this case, right, we're replacing it with a normal force. And now if we're considering friction, we've got to add that force in, force of friction. So we need to consider that along with the normal force, normal to the surface that the object is resting on, right? So this box is not just seeing this force here, right? It's seeing, it's got the weight, the force acting down. It's got the normal force, the reaction force of the surface, right? And then we've got this force of friction, which is opposing motion. This is an incline. This is what I was telling you about earlier. If you have a block on an incline, if I draw the free body diagram of this, it's going to look like this. The normal force is perpendicular to the surface, right? This is just like you would draw for a ruler. The normal force is perpendicular to the surface of contact between that box and the surface. The frictional force is opposing motion, right? So it's pointing upwards. And the weight of this object, you can see, points straight down to gravity. So from here is where we can figure out that the normal force is not equal to the weight, right? It's some component of the weight. It's that perpendicular component of the weight. Let's see. All right. Coefficients of friction. So coefficients of friction take into account the fact that two surfaces have some relationship between them that describes the friction, right? And again, this depends on the two materials that are in contact. This the coefficient of friction. And this coefficient of friction is given as a relationship between the friction force and the normal force, right? In other words, the force of friction is some percentage or fraction of the normal force. And that relationship is what's called the coefficient of friction, mu. We're going to see them related like this. Mu is the max force over the normal force. And be careful here, F max is the friction force at impending motion. This is the maximum force of friction just before the object moves. So if the object's not in impending motion or at impending motion, we can't really use this relationship. But you'll see how we can figure out those forces later on. But F max is for impending motion analysis. And we've got two types of friction: static friction and kinetic friction. So you may have noticed this, but if you were to go to try to push a, say a box, right, fairly heavy box over a thickly carpeted rug, you may have noticed that it takes a little more effort to get the motion started than it does to keep it in motion. And that's characterized by two different coefficients of friction. Mu s is the static friction. This is up to impending motion. So static friction is what you need to overcome to get this thing moving. Kinetic friction is when you have surfaces moving with respect to one another already, right? This is mu sub k. So not only do they depend on the surfaces in contact, they also depend on if the surface is moving or not. Now, most of the time, you're going to be given the coefficients of friction. You can also look them up. In fact, I think it's your textbook that has a range of, I never remember if it's this book or the other course I teach that has a table for coefficients of friction in it. But it's kind of interesting to look at, different materials. Let me see. I'm just going to really quick go in here. Angle. No. Coefficient of friction. Here, it's right here. No, it does not have. Maybe it's in the appendix. Anyway, I'll look for something before Friday. But typically, you can look them up. You're going to be given a lot of them in problems, or you can determine them experimentally. Your book uses this technique. I believe one of the homework problems asks you to look for this technique as well. Besides using the coefficient of friction, the other way you can describe friction between surfaces is this angle of friction concept, right? In other words, what's the angle, phi, between the normal force and the resultant, right? And the resultant is formed by the normal force and the friction force, right? In other words, you've got a force triangle here, right? Force, friction max, normal force, resultant force, right? Tip to tail. You can, again, translate these along their lines of action how you see fit. And this angle, right? The bigger the angle, the higher the friction, right? The lower the angle, the lower the friction, because the friction is the X component of this triangle, right? It's pointing this way. So the longer this side is, the bigger your phi is. The shorter this side is, the smaller your phi. I feel like this slide's missing something. Nope, I guess it's not. This is just basically showing you the same thing I just talked about. Now in tangent form, right? F max, if you move it down here to this side of the, or you just move it over, right? You can see that phi, or you move this over, phi is just F max, or tangent of phi is F max over n, right? So it says right triangle. Opposite over adjacent is tangent. Also, you know the relationship mu, right, is F max over n, so you can set these equal to each other. Mu and the tangent of phi are equal to one another, right? So if you're given mu, you basically know phi, you just have to take the inverse tangent of it. Or if you're given phi, you can find mu. Or you can do the force triangle balance as well. Slipping or tipping. This is where the confusion starts. So some problems are going to ask you, is the object going to slip or slide, right, first? Or is it going to tip over? Let me see something here. Oh, okay, this is an example in the, we're going to do some examples on paper, but this one just happens to be in the PowerPoint. So the example here is, will this block slip or tip? And what do we have going on here? Well, we've got a force, P, acting on the block. Oh, it looks like it should be 200 newtons. Let me just see something here. Oh, no, this is the weight. All right, that was not clear. You got this force P. You've got the forces acting equal distance, right, 4 meters. This thing has a weight of 200 newtons and a dimension of 6 meters this way. So let's look at this for a few different scenarios. Let me see, make sure the other one is, yeah. Let's look at this for the scenario of impending motion. So slipping. In the case of slipping, right, you've got a weight, 200 newtons. You've got the force of friction, the maximum force equal to the force you're applying, right? This would be impending motion. These two horizontal forces are equally balanced, right? You have not exceeded the max force, but you're just on the cusp of exceeding it. And the coefficient of friction is 0.3. So you can find the force required for this thing to slip by just solving for P. In this case, you see mu is equal to F max over N, which is equal to P over N. You can set this equal to 0.3, right, and multiply by N, which is the 200 newtons, right, because it's not a flat surface, and you wind up with 60 newtons for slipping. So this is telling you that for this scenario, 60 newtons will cause this thing to slip. Now, tipping. Tipping is, the analysis is what force is going to cause tipping. Both the normal and the friction force are going to be acting at the tipping point here, right? Again, these forces you can translate along to any of these, any of these directions, these points. The worst case scenario is you have, this corner gets, it has to overcome friction, right? And all the normal force is located there. So what do we need to do for tipping? For tipping, because with tipping, think about that. You're taking all the 200 newtons and you're putting it onto that point, right? And all the friction is also acting at that point. So you can look at this and you can do sum of the moments about A equals 0. Again, this is the point at which tipping is sort of impending. And what do we have? We've got our moment about A. Think about this. The weight of the object is directed in the center of gravity, 200 newtons. So the center of gravity is 3 meters from either side, right? We're saying that this object has 200 newtons acting at 3 meters from point A. That's the counterclockwise moment. Force P is applying a moment that could be considered clockwise about A, right? And it is 4 meters perpendicular distance from point A, right? So here's the line of action of the force, and we're given this distance 4 meters. I need to go in and relabel this diagram. So we can solve for P here, and it tells you that you need 150 newtons of force to tip this thing. Now, up here, we determined we need 60 newtons for this thing to start slipping. So what does this tell us? This tells us if I start pushing on the box and I start increasing my force, first 5 newtons, 10 newtons, 20 newtons, 30 newtons, right? I'm going to get to 60 newtons first. And then the block's going to start slipping. It's going to start moving along, right? So the slipping force gets seen first as you're increasing the forces. So this block is going to slip. Let's see, we got some examples. We have time to at least do example 1. So let's look at some examples now. Oh, I forgot to get them out of my notebook. And we'll see how that works. So the first one here, we see a crate, right? And the crate has a mass of 20 kilograms. So notice the first thing you should be recognizing here, 20 kilograms, that's not a force, that's a mass, right? Weight is a force. So I need to remember to convert that into a force. The next thing you're given is the force, 80 newtons is applied to the crate, right, as shown, and determine if it remains in equilibrium or does it slip. The coefficient of static friction is given, mu(s) is 0.3. So mu(s) is what you're trying to overcome. You're trying to overcome the friction, the static friction. All right, let's look at this on the document camera here. Oops. I adjusted my zoom yesterday for something, and now I'm not happy with it at all. All right. So what the first thing we're going to do here, what do you think the first thing we're going to do is? That we should do? Make this a little bigger. All right. No one wants to guess that the first thing we need to do is draw a free body diagram. So first, draw FBD. So draw the free body diagram. So I'm going to start off, I'm going to try to leave myself some space this time. I'm going to draw a pretty big box. I don't have much room required for the solution. Now I'm going to put my forces in. First of all, I have a normal force, which is my reaction force from the surface. I have the weight of this object. I might as well just write this out here. The weight is just mass times gravity. We're given the mass 20 kilograms. So this gives us 196.2 newtons. I have two more forces to put on this. I have this force, the 80 Newton force, which comes off at an angle of about 30 degrees. This is supposed to be a straight line. Where's my black pen here? Oh. This is 30 degrees. We're told it acts at 0.2 meters. And this whole thing is 0.8 meters. And we just need to put the force of friction in here. I'm going to draw that right here. So the first thing we're going to do here is we're going to, well, after the free body diagram. So next, assume the box or the crate is in static equilibrium. We don't know what the force of friction is here. I mean, we could calculate that from the normal force, but what I want to do is figure out what's the force needed to keep it from moving. In other words, we've got 80 newtons applied, right? What's this force of friction got to be to keep it from moving? So I'm going to look at the sum of the forces in the x direction, right? Because that's going to tell us if it moves. It's not going to move in the y direction. Right? The y direction, it's sitting on the floor. So let's look at some of the forces in x. And I'll draw a positive to the right. And what do I have here? I've got the x component of 80 newtons. So I've got 80 cosine 30, right? That's the x component there. And I've got force of friction is directed backwards, right, to the left. So that's a negative. And that's it. It's the only two x component of forces we have. So if I solve this algebraically, I wind up with F of friction is 69.3 newtons. And this is the force of friction required to keep the crate from moving. Now, the next thing we're going to do is we're going to find out what the actual max force of friction is. What is the max friction right? Well, we know that we have the equation mu s equals F max over N. We can find F max from this, right? Coefficient of static friction times the normal force. Now, how do we find the normal force? The normal force in this case is not just the weight, right? Because look, the normal force is a reaction force in the y direction. We've got 1, 2, 3 forces in the y direction, right? We have a component of this 80 newtons that's acting in the y direction. So we need to account for that. So I'm going to find N. So find N using sum of the forces in y equals 0, right? So sum of the forces in y equals 0. And I'm using upward as positive, right? Well, the first thing I have is that N is positive, right? And everything else is acting downward. I've got the weight here, right? I think I'll put this in. I'm going to write this generically. Let me put first the weight in, then minus I'm just going to put x component or y component of 80 newtons. Right, the y component of 80 newtons, the component downward. So let's write this out as an equation with values in it. The weight, oh, sorry, this is a minus sign. The weight is 192 or 196.2 newtons. The y component of 80 newtons, well, that's going to be this portion here, right? That's opposite the 30 degrees. So we're going to have 80 sine 30, right? 80 sine 30 equals 0. Basically, if you do some algebra, right, add these two up, you wind up with N. In fact, I'll rewrite this: 196.2 newtons plus, oh yeah, that's just 40 because it's sine 30. So I've got 40. N equals what? N is 236.2 newtons. Now we're going to figure out F max, right? What was mu s? Mu s was 0.3. That's the coefficient of static friction. And the normal force is 236.2. And, well, I already have the number here. That gives us 70.86 newtons. I'll round that in a minute. Now, let me see here. All right. The force of friction that we need to keep this thing from moving is 69.3 newtons. The maximum force of friction we could expect to get is 70.86 newtons, right? So let me just write a little inequality here. F of friction is less than F max. So the crate Let me put a poll up. Yes, no poll. Do you think the crate will slip if the max force that we got here, 70.86, is greater than the force required to keep the crate from moving? Will the crate slip? So yes or no, will the crate slip? I don't know if anyone's paying attention. No one's responding to the poll. There we go. We're getting responses. Will the crate slip in this case? We have 4 responses. It's 33% of you. It's low turnout today. Everyone else is taking the test, I guess. Look at missing out on the fun polls. 5 people. Hey. I'll give another 30 seconds here and I'll close it up. Again, this is kind of the part where people overthink and, well, they think themselves into the wrong answer. All right, 10 seconds. I'm just going to end the polling now. Not bad. 8 out of 12 people. So let's see. 6 out of 8. 75% of you said it will slip. And this is what I'm going to have to focus on here. Let's look at. I'm going to close the poll results. Let me walk you through the thinking here. The maximum force of friction that we can expect to see is given to us by this relationship. The coefficient of friction times the normal force. Right? We figured that out. That's 70.9 newtons, right? This is how much friction we need to overcome. Up here, we did the analysis of how much friction do we need to keep this thing static, stationary, not moving, right? That turns out that we only need 69.3 newtons. So we need less force to keep it from moving than to overcome friction to cause it to move. So in this case, the crate will not slip. Because we have more than enough force of friction to keep it from moving. $44. Oh, this is a slipper tip one. Yeah, I think one thing to notice, let's just discuss this for a minute. If I had a smaller coefficient of friction, right? If mu(s) was 0.25, right, what would I get then? I would get 236.2 times 0.25. F max would be 59.1 newtons. So this would be the opposite scenario. Then the crate would slip. And why is that? Because up here it's telling us that 80 newtons of force requires 69.3 newtons of friction to keep the crate from moving, to keep it stationary. Well, if our coefficient of friction was less, right, like 0.25, we would only have a maximum force of friction of 59 newtons. And that would not be more than the force of friction, right? So in this case, force of friction would be greater than F max, and the crate would slip. Yeah. Are there any questions about this that I might, if you have, that might help me clarify this for you if you're not getting it? Otherwise, I'm going to stop here. And again, I'll stay on for questions for a couple minutes if there are any. But we'll pick up here with friction on Friday. All right. Everyone have a good Wednesday.